All right. So just a quick run through before I give you any notes, right? We should know that all magnets are generally they have two poles, north and south. All right. Around the magnet, there's something called a magnetic field, right? And the magnetic field is what we kind of feel and experience, right? You might not see it, right? But there's an electric field around it, right? If we wanted to determine what this magnetic field looks like, we could use something called a plotting compass, right? And the plotting compass will give us an idea of the direction of the magnetic field around it. Okay. So for example, if I put a paper clip here, while I'm to that paper clip, it will be attracted to the magnet, right? So there must be some field or some force pulling it towards the magnet, right? Suppose I put the paper clip real far away. Would it be affected by the magnet? No. So it means that this magnetic field has a limit, or it has a range in which it will have an effect, right? So to determine the magnetic field and where it operates, we could use something called a plotting compass, right? That's like the small compass there. In fact, I could bring some for to play around with it and see. All right. And you'll be able to see how the magnetic field works, right? Actually, I'm going to do that now. In fact, let's watch a simulation. All right, so what you see, right? There's no magnet, right? So it behaving, right. So what you have there, those little things there with the red and the silver, right? That's a plotting compass, right? If I were to bring the magnet in now, you would recognize that it behaves a certain way. You're seeing that? What you can see is happening to the red part of the compass. Huh? The right. So it appears that the red part of the compass is moving away from the north and it's attracted towards the south. You're seeing that? So it's moving away from the north and it appears to be attracted to the south. Right? If you all look at a plotting compass, that red part is like a little arrowhead. That's like a North Pole there. So what that's telling us is this. It's telling us the direction of the magnetism. It's telling us the direction of the magnetic field. So if you look at the arrows here, you will see that the magnetic fields move away from the North Pole and they move towards the South Pole. Okay, so that's basically how magnetic fields will look. You have a north and a south. They'll move away from the north and they'll move towards the south. Away from the north towards the south. You'll see that? Right? So that's the way magnets will behave. Move away from the north and towards the south. Magnetic field, sorry. Suppose on the other hand now, we decided to bring what's this here? Right? This was a 3D version of it. I'm not sure if you've seen it. So good. Right? That's like a 3D version of it. Seen it? Yeah, that's a 3D version of it. Tell me what you think will happen here. In fact, draw that from head up magnetic fields and draw that diagram. That's the magnetic field direction.
Yeah, I believe that. Not as is this. What are you? This is like.
And you say before the store. Of course, it's not as much. But I don't. Yeah. Yeah.
Yeah, the magnetic field, but something missing on those magnetic fields. Right, this. Something missing. Arrows showing direction, right? The mark paper now, just put the arrows there, showing direction. Right? And the direction is what? Magnetic fields always leave the and go towards the south. So the magnetic fields will leave the north. And everybody coming where? South. See? Everybody loves south. Right? All right, nice. So we learn about magnetic fields, we learn about their direction, we learn about how they look. One last thing before we bring magnets together. Think we're good whole day, boy. Probably tired or? Huh? That's a viewer, something. All the thing we're good whole day. And the place cool. Wait, I got log off there. Online. You all see anything now? No, it blank out. Hold on, eh? All right, good. Come back fast. So what you see in case it cut off again. What you would recognize is that close to the magnet, you see how many field lines in that little circle there? And then far from the magnet, like somewhere here, same area, you see less field lines? Yeah, that is called magnetic flux. So here, you have magnetic flux, right? This is high magnetic flux. Here is low magnetic flux. You'll see that? So we have high magnetic flux and low magnetic flux. Okay, so let's make a note on the diagram, make a note of where it's high magnetic flux and low magnetic flux. All right, so good. So that is your magnetic flux and thing there. Nice. Now let's see what will happen when we bring magnets together. You all see in this one here, right? I'm going to bring a next magnet next to it. What does normally happen when a north and a south comes together? Attract, right? Unlike poles, but like poles, you all can see why, watch this here. You all can see why attraction happens because the field lines actually interacting. So it's like two people that like each other and they're actually talking and they're interacting. Malakas, boy, about you, boy. Right? Are you okay with that? So that's the attraction there. So unlike poles attract, let's see what will happen. let's see what happens like that. And it's not perfect, but look at the felines. Are there any interaction? Right? So Malachi called on the girl, but the girl not answering she phone at all. She didn't answer she phone at all. She had nothing to do with, right? So they're not interacting at all. Okay? So you would recognize there that no matter how close you try to bring the magnets together, they're not going to interact, right? And that invisible force in the middle are the felines that not interacting, right, Keanu? Everybody okay with that? All right, so here's what you're gonna do online. You're okay with how the felines will look? Sahara, Katrina? Are you okay there? All right. Yeah. Okay, let's do my favor now, please. Draw the felines, man. Draw this one. This is repulsion. Unlike poles, right? Draw that, please. Then I'll flip it and you'll do like poles. Sorry, this is like poles. I will flip it and you'll do unlike after. Tell. Well, here, I need to talk a little louder. You hear.
Nikolai Batiste, this is Rami Durai and
Hey, wait. And this
Hey, what
voice.
you seen, Ravi? You see?
Okay, okay. Yeah, you say hello. This boy is supposed to be in Max, huh?
Nikolai.
No, Nikolai. Nishad. Huh?
You like to offer yellow, you know,
Oh. I will send the September timetable in the group, so I have that as well, right? Okay. I'm on.
It's all right. You know, pretty much. You want to know, Judy?
Can't believe that Malachi. Right, on your diagram. On your diagram, you can draw this one already. You can draw this one? Get to draw it. This is for like No, that's what one magnet, that's what one magnet alone. This is for two magnets, interaction of two magnets, right? Go take a picture, draw it. Oh, and put in the P lines, right? Sorry, put in the arrows. Put in the arrows moving away from the north and toward.
I can be honest.
No, I really got it. No color, I think I got it.
Right, so drawing man, put the arrows, right, away from the north and towards the south. Oh. Right, just make sure it don't interact. I didn't hold this for, not sure. Good stuff, really. All right, next one. I changed it right because I wanted to get a diagram quickly. Right, go ahead. This is unlike poles. Do unlike poles quickly. Unlike poles. Sorry. Yeah. Light poles. That was like north. That was a north and north or north and yeah, that was north and north. Maria, are you okay there? Right, so in exam, of course, you have to be able to redraw these things, right? Unlike poles. Right, like poles repel, unlike poles attract. And the reason for the attraction is the magnetic fields actually interacting with each other. Right, again, it missing arrows, put in the arrows, right? Put in the arrows, please. Harisha, what's your last name? Right, anybody join cell? Anybody join cell? Harisha, you could just send me your last name, please. Harisha, you there? Yeah. Oh, next, oh, that's Carisha, okay. Oh, Mrs. Crawford. All right, good. Everybody okay there? All right, so let's just take a look. Let's just take a look at what will happen if we have two U shapes. See how the U shape looking? It makes sense? Not going to south. Y'all seen it? Let's bring our next U shape here. Let's flip this new shape around. That makes sense? North and north interacting. Sorry, south and north interacting. North and south. Y'all seen that? All right, now I was trying to just flip it there for you to see. But it's the same principle, right? North interacts with south, south interacts with north. If it were north and north lining up, then it would then they won't interact, right? Kind of like that. You see how the south still trying to interact with the north, right? And the north on the second magnet too far away from the south on the left, right? So that's why there's no interaction. All right, nice. That's for us to see that. Let's take a look quickly at something called magnetic induction. Right, we're just trying to paint a good picture of everything that we're going to dive into, right? So look at what happened. What happened to that small nail? Right, and something else. Watch again. Huh? Something else. Was that it? Right, but does our nail have a north and a south? No. So look closely at what's happening here. Right here, it's attached to the magnet, but something else.
When it connects to the north, it automatically like
Right, it became a magnet. It is, so it's called induction. So it was induced magnetic properties, right? So one end became south and one end became north. That's okay. So this is called magnetic induction, because if I move it away, it's not a magnet. You recognize that? So induce gives it temporary properties. Okay. Now it's temporarily a magnet, right? So if I bring this fella here, he became a magnet as well. But if I move him away, he's not a magnet. What up? I bring the next nail there. He becomes a magnet as well. But is he as strong? You can't see it there. But is he as strong? No. Right? The lower you go, the weaker the magnet becomes. All right? You get on some magnetic induction, right? So induction, you remember we did induction somewhere. But where we did induction. This is magnetic induction. We did electrostatic induction, where you had positive and negatives on it. Yeah.
Yeah, I remember.
All right, nice. So we learned about magnetic induction. I wanted to show you one more. All right. There's one more I wanted to show you.
So yeah, that's right.
Yeah.
So okay, if I have a screwdriver, a metal screwdriver, and I rub it on a magnet, and like this, like if I want to get a screw, if I just rub the screwdriver on the magnet.
For a short period, it becomes a magnet.
Yeah.
For a short period, yeah.
so it's like when you electrostatic, when you rub it, depend on the head.
Kind of the same thing. Kind of the same thing. The paper becomes temporarily charged and then we to pick it up. Right? It also works with it also works with creating a magnet. If you take a magnet with the right material, right, and you pass the magnet long enough, after a while it becomes magnetic. Well, longer. It'll become magnetic for a longer period of time. All right, I just want to show you an application here. Watch this here. This is electromagnetic induction. So it means that the magnet given electrical properties. That's okay? So watch out there. Is that bulb lighting right now? No. But if I would, you all know what generator is? A generator runs on the same principle. We have no electricity, but by turning or moving a wheel or something, you'll be able to get electricity. So watch this here. If I take the magnet, wait, I can't move it. If I move the magnet, well, close to the solenoid, continuously move it, see what's happening? See what happening there? The bulb lighting up, right? Same principle, right? We inducing electrical properties onto the wires and bulb. Okay. Watch this here, right? Well, when the field lines get close to it, the bulb starts to light. See that? When it's far away, now it lighting. When it comes close, lights. Are you okay with that? So we have magnetic induction and we have electromagnetic induction. Right? Nice. So all these simulations showing you how magnetism plays a role in everything, right? What is generator here? See that? Yeah, a piece of wire and it turning between a magnet, causing the bulb to light. Okay, that's a generator. Of course, we have rules to learn, right? I want to show you one more. Hold on. Okay, I'm not saying it. All of the home wiring circuit here. I'm also looking for this. So remember, for next time it's on the Java lab, right? All right, nice. Okay, let's head back into some notes something now. Okay, nice. So let's just go back here. I wanted to write a small note for my, it just gives you a definition for some of the things, right? I am redoing this handout, so I'll probably give it to you next week. All right. So that's why I'm making you write these things out. Selena, you okay? Write this in my paper. This is a little note I was giving you earlier. Write this, please. Just a note. You have to write in diagram. I just copy down the note there. Okay, we're done. Oh, yeah, fine.
Yeah, this was distracted, sir. Making it hungry, yeah. So you want to take a ride over? I have some advice on that. Yeah,
Ready?
Yes.
Right, so this is the intro. This was a magnet, the pole direction and how magnetic fields interact. You all recognize, right? Every single time you bring two magnets together or two magnetic fields together, you gain a force, right? So we'll be going to learn a little while about left hand rule and right hand rule and right hand grip rule and things. Okay. What?
Don't tell him when. Ask your
I know what you say. Was it grip rule? Oh. That's what you say? I thought that's what you said. Right. Anybody writing? Anybody writing online? Taking it off, right? All right. So now, so we learned about anybody remember this? What is go from division to multiplication to subtraction? Of course, huh? You remember that? Yeah. Long division of polynomials, yeah. Right? Remember you divide and multiply and subtract. What kind of remember?
Yes, sir.
All right. So here's what we're looking at now. For Malachi's talking, right? We're looking at current carrying conductors, right? So if you have an electrical circuit, right? Those current carrying conductors, those wires with current in it, actually there's actually a magnetic field around it. So for example, those wires carrying electricity, there's a magnetic field associated to all of them, right? They all have magnetic fields around them. That's why sometimes they see like those high tension wires, right? Those high tension wires, you can't put anything metallic close to them, right? So even if, so like for example, if the wire is here and you have something metallic, even if it comes close, it will interact with the magnetic field around it and it can still end up getting electrocuted. So it does not have to touch necessarily if it comes close. Okay, and you interact with the magnetic field around it. Okay, so we are going to take a look at current carrying conductor. Right, the reason I'm sending a handout for this one, we want for this not to be over, right? So I'll send it over. Right, so current carrying conductors. Let's say we have something like this. We have electricity flowing, we have the supply, we have a load somewhere there. Right. What direction current flowing in again? From where to where? You see it? Current flowing from where to where? Current flowing from north to south. From the positive to the. What side is the positive? What side is negative? Positive, negative, right? And current flows from the positive to the negative. So you'll see from coming north to the south. Okay, now around the current carrying conductor, there's a magnetic field. So the first rule that we're going to learn, watch Malachi. So smile already. I'm nasty man. Right, watch. Right? Watch. It's called the right hand grip rule. So your thumb points in the direction of the current, and your fingers point in the direction of the magnetic field. Okay? So current going where? Current going down here. So your thumb is going to point downwards. Okay, and your fingers pointing in a circular fashion like that, right? It's a little bit hard to see here. That's the reason why I'm going to show you in a different orientation, right? But it going down and it coming around in circles like that. That's okay. So it coming around in little circles like that, and I took over the 3D diagram, right? Right, by looking like that. Right, around the magnetic pole, there are these circles. Okay, but to make it look a little bit simpler, here's what it did. Instead of having it parallel to the board, they put it perpendicular to the board. So they put a little circle saying that the wire could be going into the board or out of the board. Right? So picture the circuit like this. Current could either go into the board or out of the board. You're seeing that? And instead of flowing on the board like this, what they did is they tilt the circuit, right? So therefore the current can either go into the board or out of the board. So it's easier for you to see the magnetic fields. So let's say X represents in and a dot with a circle around it out. So this is current going in. And this is current coming out. Okay, and the rule that we're using is the right hand rule. Some people call it Fleming, some people call it Maxwell, but different guys get that. They got right, let's look at joy fair. Right, so it looks something like this, right? So your thumb, right? Your thumb gives you direction of the thumb gives you the direction of current, and the fingers, all these fingers here, direction of magnetic field. Okay, and this whole thing here is called the right hand grip rule. Okay, So how are we going to use it here? Watch this here. How are we going to apply that rule here? Right? Watch it. Right hand. Current going in, current coming out. So your thumb points in the direction of current, right? So your thumb going to point inwards. What direction current flowing in? So sorry, what direction the magnetic field in? In a clockwise direction. See that? So your thumb going in and your fingers pointing in a clockwise direction. So this here is your, I'm gonna change the color. I'm not sure if you'll see this online, but magnetic field is in a clockwise direction. That's okay. Right? You might be able to see this, but clockwise is it. Clockwise is a south pole. What do you think this one will be? That'll be anti-clockwise and a north pole. So, okay with that? Go ahead, have fun, copy it out. Make sure you're having fun. If you don't want to, if you're not having fun, do copy this on. No matter, it's one. Okay, boy. Your favorite, this would be a favorite rule.
Nasty.
Left hand rule.
Yeah, please.
Right, so you're going to learn all these rules, right? Left hand rule, Fleming's left hand, Fleming's right hand, grip rule. Okay, those are all the rules I'm going to learn. Copy it down.
Really? When you come out, when you come out, I you tell it. I think that. No, they were in like go. I pay. Look. Try to remove. Bring it here. Bring it here.
Oh, it's oh yeah.
No person back and taken it. I. One hundred and 40. Hey, relax. You know, one more. Yeah, maybe. Yeah. Now it's serious. I think he didn't get access. I take. I can't see all the 5.
Who have the remote?
You what?
Who have the remote?
We looked at but we didn't see it.
I like.
No, serious. Tell me, yeah.
Who have the remote?
Yes.
Don't put in cut off.
Sir, I don't check it one. Check it one. It's fine.
Well, put it.
I don't know. We really come here to look at this stuff. It was right here. Oh yeah. All right. Well, making one here, guys.
All right. All you have this right, north and south.
Oh shit! Oh shit! Oh sir.
Yeah.
What? What's up, right? But we gotta shoot it.
Everybody have this?
Yes, sir.
All right, so I like to play. Huh? All right, so good. So that gives us an idea of what the field lines will look like, right? So this is first rule that you're going to learn, right? There are 3 rules. Right hand grip rule that you're going to use twice. Left hand rule, right hand rule. Okay? Right? We'll do this next week. Next thing. Right? So good. This is the first application of right hand grip rule. All right? So this is current carrying conductor. Take a small note on underneath this. Current carrying conductors. Current carrying conductors.
No, serious. I'm serious. I'm no, seriously,
Right. Current carrying conductors have an associated magnetic field around that. Current carrying conductors have an associated magnetic field around that. Have an associated magnetic field around them. Full stop. The direction of this magnetic field is given by. The direction of this magnetic field is given by. The direction of this magnetic field is given by the right hand grip rule. By the right hand grip rule. as shown above, right? As shown above. First up, if the current carrying conductor is shaped into a solenoid, if the current carrying conductor is shaped into a solenoid, Fleming's right-hand grip rule can also be used to determine the magnetic field. If the current carrying conductor is shaped into a solenoid, right-hand grip rule can also be used to determine. Right-hand grip rule can also be used to determine the direction of the magnetic field. The direction of the magnetic field. All right, so watch this here. What is a solenoid? Right, you would have seen a solenoid is like taking the wire and turning it into a spring. Right, so a solenoid looks something like this. Watch this here. This is a positive, this is a negative. Are you okay with that? For a little bit, that's all. I want to make sure you can see. Right, so current flowing this way. Right. So current flowing upwards here, and then we'll go through here and come downwards here, right? Okay then? Right. So watch it here. So the current now, if I were to turn it into a solenoid, it will go in here, come out at the bottom, in at the top, out. You'll see that? In at the top, out. In at the top and out. So it's going, the current going in here and then coming out here. It's going in here and coming out here. Right? You'll see that? So current all the time, it's going in at the top. What's the symbol for current going in? Right, X. Correct? So all the time on top of the solenoid, it's going in. What about underneath? Out, right? So you put it up with it also. Right? And here's how Fleming's here's how the right-hand rule could be used for finding the direction of the magnetic field. So you same right hand, but the difference is your fingers, right? These fingers point the direction of the current, and your thumb points towards magnetic north. Okay, so your fingers, right? Your thumb will tell you where magnetic north is, and your fingers will give current direction. Are you okay with that? You're right. Watch here. I want to make sure you understand this, right? So current going in at the top and coming out at the bottom. So watch your hand, right? Your hand will go in at the top and come out at the bottom. You're seeing that? And your thumb pointing where? Towards magnetic north. So your thumb telling you that here's north. Here's south. That's okay? And we know magnetic fields leave the north and they go into the south. They leave the north, go towards the south. That's okay, and you can just connect them up here if you want. You're saying that? So we know where north is, a magnetic field is leaving the north and going to the south. Leaving the north, going to the south. So that's the way you figure out the magnetic field on a solenoid. That's okay? So you're kind of using the same rule, but in reverse. Your fingers are now current, the thumb is not. Okay? For the next rule, for the straight wire, this is current and this is magnetic field. Are you okay with that? Okay? Show this one. This is the harder one to remember, right? So that's it. So today we learned about magnetic fields, field lines, the interaction of magnetic fields, and we learned about magnetic fields around current carrying conductors. Next day, what we're going on to do is we're going to bring the magnetic fields together. We're going to bring this magnetic field next to our magnet. Okay, take your time, do all of this, everything, write this back. Write this, everything, all this here, this too. To look for the shortcut, please. That's the weeks, everything.
No. Oh, I feel like we're ready to it out. I don't know, like that. I think I'm ready to. I still don't have to. If you already reply. Yeah. I don't think. Whenever it's not, can I say? How is your now? Who is it? Yeah, we have to give them a how is it? Oh, it is very cool. Oh, that is my code. Yes, I want to.
So very cool for us to say quick. Tell them that way. We fast now, how it works. Quick. One idea. Muhe देखते मत चल और नहीं फिर वाले से बात there are some money.
Alright. Good. Okay.
Sorry, now wait. Hold on. I want to join you. I want to check. I want to put something.
No, sir,
We can't join. I told you, online. That's it there. Once you